In this short video, I'm going to show you how flow sensors work and how you can implement them in an irrigation system. I'll also show you a handy device that I've created that allows you to convert any pulsed output flow sensor into a voltage so it can be read by virtually any data logger. Finally, I'll show you how to connect a flow sensor to an irrigation system. A flow sensor is a device that measures the flow rate of a fluid through a system. They're commonly used in irrigation and hydroponic systems to detect leaks, bad valves that are either stuck open or closed, and to calculate the total volume of water being dispensed. They can also be used to detect pressure changes as the water is flowing. There are several types of flow sensors that operate on different principles. The first type is thermal. These have an upstream heater and a downstream temperature sensor. As the flow of fluid increases, the detected temperature changes, and that change can be correlated to flow rate. These sensors have no moving parts, but they're expensive and often require calibration for ambient temperature and fluid type. The second type is ultrasonic. These measure the time or phase difference between a transmitted signal and a received signal, typically pulses. As flow rate increases, the time between sending and receiving the pulses changes. The simplest and least expensive type is mechanical. These consist of an internal turbine, a magnet, and a Hall effect sensor. As water flows, it turns the turbine, which rotates a magnet. The Hall effect sensor detects this rotating magnet and outputs a pulse for each revolution. The faster the pulse train, the higher the flow rate. I'm going to focus on this type of flow sensor because it's the most affordable and commonly used. This is a Vegetronix 3/4 inch brass flow sensor. I've hooked it up to a breadboard and an oscilloscope so we can see the pulse train coming out of it. The output of the sensor is an open drain transistor, so it needs a pull-up resistor to produce a voltage. I've connected the oscilloscope ground to the negative side of the circuit and the probe to the junction between the sensor output and the pull-up resistor. It's powered with a 9-volt power supply. By the way, I'm Tim, an electrical engineer who applies engineering principles to gardening. If you enjoy learning how science and engineering can be applied to gardening, please subscribe. I'm going to blow into it so you can see how the pulse rate varies with the flow. You can see as I blow harder, the pulse rate increases. To convert the pulse rate into a flow rate, such as liters per minute, you need to do a little math. The first step is determining the pulses per second from the flow sensor. To do this, you'll need a microcontroller or data logger with a pulse type input. Once you have the pulse rate, you can calculate the flow rate. For this particular flow sensor, the flow rate in liters per minute is the pulse rate in hertz divided by 6.6. For example, if you measure 6.6 pulses per second, that corresponds to a flow rate of 1 liter per minute. If you want to dispense an exact volume of water to a plant, the math is straightforward. Let's say you want to dispense a half liter of water. That means you need to run the system for 30 seconds at a flow rate of 1 liter per minute, which results in a total output of about 190 pulses from the sensor. While every data logger can read voltage, not every data logger has a pulsed input. That's why we've created a handy device that converts the pulsed output from a flow sensor into a proportional voltage. This allows you to connect the sensor to nearly any data logger or controller. I can plug the sensor directly into the pulse converter and will monitor the voltage output as I blow into it. You can see the voltage increase as the pulse rate increases. Let me show you a real-world application. My property is connected to secondary irrigation water that comes from a central pump in my neighborhood. In the summertime, the pressure can greatly vary depending on the neighborhood usage. Since the flowing water pressure is related to the flow rate, I can monitor the pressure of the whole system when my irrigation is running with a single flow sensor. I'm hooking the flow sensor up to PVC couplings. I'm plugging the flow sensor into a pulse translator in a waterproof enclosure. and the translator is connected to a Veggie Hub Wi-Fi logger powered by batteries. We'll conveniently mount this on a PVC mast and install it in the irrigation system. I've hooked the flow sensor into the drip irrigation system of my vegetable garden. The sensor sends pulses to the translator, and the pulse translator converts them to voltage and sends the voltage to the Wi-Fi logger, and in turn, the logger sends the data to veggiecloud.com, where I can monitor the flow rate. Lastly, I should mention that there is one drawback to turbine-based flow sensors. If the water is dirty, debris can clog the turbine, which can be an issue in gray water systems. To mitigate this, make sure you use water filters. You can also consider oversizing the sensor by installing a larger diameter flow sensor in a section of the pipe, since larger turbines are less likely to clog. In my next video, I'm going to hook up a flow sensor to my garden hose. My kids use it and constantly forget to turn it off. It's next to a window well, and I'm worried it's going to flood my basement. I want to get a text message if the water is ever left on. You can see this video by clicking on the video link here. I'm curious what you think. Have you tried something like this? Let me know in the comments. If you've made it this far in the video, I guarantee you'll enjoy my other videos, so you might as well subscribe. Also, check out Vegetronics.com for cool gardening gadgets and automation ideas. Thanks for watching.